there are two important consequences of the law of cosines that allow us to calculate the area of triangles much more easily than we did in our strict geometry classes. In geometry, we use the formula 1/2 base times height to calculate this. And when working with triangles, we had to do a lot of dropping perpendiculars and figuring out those heights. And that made it very, very difficult. But using the law of cosines, we actually can get an area of a triangle formula that becomes A equals 1/2 AB sine gamma, or area equals 1/2 BC sine alpha, or A equals 1/2 AC sine beta. And hopefully you see some similarity between these area of a triangle formulas and the law of cosines, that we've got that side angle side scenario going on, that in all three cases we have two side lengths and we have the angle that is between them. But we're taking the sine of it, and there's a derivation of it. I'm not going to go through that here, but this is the consequence. Another way to say this, if you wanted to do this a little more generally and you wanted to say this in words, you could say that the area of a triangle is 1/2 the product of any two sides and the sine, S-I-N-E sine, of the included angle, meaning the angle between them. And that's what all three of the formulas say. I just put it in words because maybe you don't memorize the formula, but you can remember the idea. One idea covers all three formulas. So just a really useful thing to have for finding the areas of oblique triangles for the side angle side situation. So let's just look at an example of using these formulas. Oh, that's the wrong direction. So approximate the area of the triangle ABC if A is 2.2, B is 1.3, and gamma is 43.2. So we're using our triangle still in the conventional sort of labeling situation that we might have. So if I have some sort of triangle, let's just make some sort of random triangle A, B, C. So the side length A is 2.20. B, directly across from B, is 1.30. And gamma is 43.2 degrees. So gamma would be the measure at vertex C. So I've got this side angle side scenario. Since this is not a right triangle, we used to have to do things like drop perpendiculars. Sometimes they're inside the triangle, sometimes they're outside the triangle, to find the height, and it gets very, very difficult. Now with trigonometry, we can simply follow the formula and say that the area is going to be equal to 1/2 the product of the side lengths multiplied by the sine of the included angle. And really, it's just a matter of taking this, putting it into the calculator, and getting an answer. And you put that in the calculator, take a minute, and we get approximately, should put approximately there, 0.98. And we have a units on here, centimeters, so that's going to be square centimeter. And so that's a pretty easy formula to use. You know, maybe, let's see if I have another example here. I do, I've got another example here. Approximate the area of ABC, where I've got A, B, and alpha. So this might require a little more work to figure out what's going on based on the information, using the law of sines and the law of cosines to get us there. So I might have some triangle A, B, C. Alpha 37 degrees, A is 5 and side B is 3. So I can see here that I have two sides and I have an angle, but I don't have the included angle. I've got two sides and an angle. Based on this, I would probably want to know, based on knowing two sides A and B, I would be most interested in figuring out the measure of angle C, that measure of gamma there. If I can figure out the measure of gamma, then I can go ahead and use the area triangle formula, side angle side situation. So I'm going to go through that, but I don't think I can find C directly. I'm probably going to have to use the law of sines using my complete ratio. Sine of 37 degrees over 5 equal to sine of beta over 3. So I'll do some work so that sine beta equals 3 sine 37 degrees over 5. I'm looking for an angle, so it seems to me that I'm going to have to use the inverse trig function. So the inverse sine of 3 sine 37 degrees over 5 will give me my beta. Now it's just a matter of taking that expression, putting it into the calculator, using the inverse trig function. And when we do that, you can take a moment, pause the video, and do that if you'd like, see what you get. But in the end, we get about 21 degrees. Since A is 37, alpha is 37 degrees, and beta is 21 degrees, I can now figure out gamma by saying 180 minus 37 minus 21, which is really 180 degrees minus 56 degrees. So that's going to give me 120. Oops, that's not 56 degrees. That's 58 degrees. So that's going to give me about 122 degrees on gamma. So now I've got my gamma. I can scroll back up to my diagram, and I can use my area formula and say that the area is going to be 1/2 5 times 3. I'm going to be out of room now. Let me slide this a little bit. Times the sine of the 122 degrees. Just a matter of putting that into the calculator, and we get approximately 6.4 square centimeters for our area there. So we like using that area formula, and like a lot of things in math, the tasks ask us to find the area of the triangle. We may not be able to directly go into it. The question is, to use the area formula, I need a side angle side situation. I was not given a side angle side situation. What techniques and formulas are available to me to create that side angle side situation? And those would go backwards to using the law of sines, the law of cosines, angle sums being 180, and a variety of things like that. Right? So that's one way of finding the area of an oblique triangle. So that is hopefully much easier than what we did in our geometry classes when we were dropping perpendiculars from one side to the other.